My name is Jacob Huang. I'm the acting director of IAS. So welcome all of you come from the CDU, IAS. So today we have a great honor to invite a very famous mathematician, Professor Zhang Shou-Wu, yeah, in Chinese, Zhang Shou-Wu. Professor Zhang graduated from Columbia in 1991. I think so, right? Okay. Before that, I don't have any information. Yeah. And not CDU, right? Yeah. Anyway, and then he was invited to be a member of IAS in Princeton, the most famous IAS in the world. I think started from Einstein, a very famous scholar, from 1901 to 96. And also he was an assistant professor in Princeton University concurrently. And after 96, he joined the Columbia University from 96 to 2011. So that's been a while in Columbia University. And then after 2011 until right now, he since went back to Princeton, right? So you have a very like a dual obligation, both in Princeton and Columbia, right? Very strong relationship, okay? And Professor Zhang is famous for his research in the area of numbers theory and also algebral geometry. Yeah, he probably will mention what that is, okay? And also he's the among the editorial boards of many famous journals like Algebra and Numbers Theory, From Mathematics, and the Science in China, and many others. And Professor Zhang was the very honored invited speaker of the International Congress of Mathematics in Berlin in 1998. And also he was awarded a gold medal of mathematics in the International Conference in Chinese Mathematics, also in 1998. And also he received the Guggenheim Foundation Fellowship in 2009. And also he was elected as a fellow academician of American Academy of Science in 2011. So I think once you receive the fellow, then you were sort of recruit back to the Princeton. Yeah. Is that any special connection? No? Yeah. So that means when you receive some award, you'll be recruited by some other university or institute to a higher position. Yeah. So anyway, Professor Zhang is very, very famous, and today he's going to present the L function, its past and the future. So let's give a warm applause to Professor Zhang.
Thank you very much for a very nice introduction. And the reason I went back to Princeton because there's a crisis. Everybody left, including Andrew Wiles. So they asked me to go back. So, and then I left. I told Columbia that Columbia is already very best university. So there's nothing I can do for them. Well, I mean, it's very nice to come to this IAS to give a lecture. Somehow my life is always associated to IAS. Right now, I live in the IAS. And in Beijing, I visited the IAS of Tsinghua University. In Hong Kong, always be IAS in Hong Kong. Hong Kong UST. So somehow, I only work at IAS or live at IAS. Okay, so I want to give a lecture about error functions. It's the past and the future. This error function is a very interesting mystery subject in mathematics, in particular in number theory. It appeared very early in calculus 1, right? So the P functions you study when you study the convergence of the then the first exercise you want to do is the P series. But somehow somehow it's a very natural calculus rule, calculus object. it becomes a subject in number theory. It's not that nature. So my whole point of my lecture is trying to say this actually is a nature subject. Before I said that, I remember when I went to, I did my undergraduate in Sun Yat-sen University, Zhongshan Dahou. And there, I remember I first want to read the proof of a Goldbach conjecture. So I read the book by Pan Chengdong, the Pan Zhenbiao. So that appeared the error function. I really get annoyed. So because the thing is so complicated, so I threw the book away. So this is completely ridiculous subject. So many years later, I realized that. So the error function is so powerful, there's no way to avoid that. So nobody likes the error function, but can you find something better for that? So today I try to talk about the past story of error function and the future, and I miss the present because this period, this needs several workshop or conference for what we're doing right now with error function. Future is easy to talk, it's just a dream, right? Past is already done. So let's go back to something we know in elementary school. For smart kid, for usual kid is the middle school. So we're trying to add the powers of sums. So they're giving the k, trying to add 1 to the k, 2 to the k, 3 to the k, to the 1 to the k. Right? That's something we know. For smart kid, no, 1 plus 2 plus 1, 100 times, that's 100. That's basically it's a definition. For smart kid, you know you can add 1 plus 2 plus 3 plus up to 100. Then they already have a beautiful story about Gauss, how he could solve the problem when he was very young. You can go in, I don't know, you never challenge a smart kid to add 1 square plus 2 square up to 100 square, right? Not so many stories about this thing. So then we can add more. 1 to the q, 2 to the q, to the 100 to the q. You get more complicated. Okay, so the question will be, for a positive integer k and n, is there a formula for these sums? Oh, I'm sorry, there is something missing. This 100 should be n. So when this exponent is 1, again, it's just a definition. When this n, the exponent is 1, this is actually the formula of a Pythagorean. It's more than 500 years BC. And then, of course, the story we told by teacher is Gauss discussed the formula. That's not true. It's much earlier than Gauss, right? And for square, 1 square plus 2 square up to n square, that's done by Archimedes. It's 250 BC. It's pretty early. So, but still, it took many years, almost 300 years. But of course, you don't believe this story, right? Probably somebody in the middle did something, but Archimedes is so famous. Then for the third power, 1q, 2q to the nq, then this just happened to be the formula first one square. This is done by the Indian mathematician, Arya-Hatta. That's already 476 AD, so it took many years. Well, so what is the general formula? You can do this way. This is the question. I think for any students in the middle school, you're curious about that. Do they have a general formula to do that? And what do you mean the general formula? So the story is there, of course, the Fermat, Pascal, Bernoulli, everybody knows there's a general formula. So, well, mean that if you, for any n and a k, there will be, this sum is actually a polynomial in n with a degree at most k plus 1. Right? You can say about that. So you have these coefficients. The question, can you find this coefficient? And I learned this formula when I was in middle school, read a small book by Hua, they call it Induction. mathematical induction. I guess probably many of you in my generation got this book, right? It's a book give you induction. But book didn't really tell you how the formula come from. Just say, with the induction, you will find the formula, right? So, but the history recording this formula is in a book by Art of Conjecturing. So the Art of Conjectures is given by the older Bernoulli, Jacobi Bernoulli. So in the Bernoulli family, there are three very famous Bernoulli. The older generation is the older Bernoulli is a pharmacist, and he has two sons. One is Jacobi, one is Johann Bernoulli. So this is Jacobi Bernoulli. And he wrote this book called Art of Conjecturing. Is considered as the mother book of the modern probability and combinatorics. So in this book, he introduced his famous Bernoulli number. Then he gave a closed formula for this sum of the case power of integers up to any n. The formula is not easy, not difficult to write down. It's simply this combinatorial formula plus Bernoulli formula. If you find it very difficult to remember, then you put this formula like that, right? You just think about the b to the case power instead of up index, become low index. You'll get it. And there's another way to write down these sums using the Pascal triangle or the Yang-Hui Sanjiao. So you do this thing, but instead of a sum, you do the difference. But it's more the same. You get the stuff. Because the reason is when you prove this formula, you always use the induction. So you do this thing, you get a bunch of integers here. Then the relation between the coefficient of this in the Pascal triangle or Yang-Hui Sanjiao is related by a matrix. So you put these numbers in this way, put this number this way, the inverse this matrix go with the other one. So it's a very simple formula. You don't even need a Bernoulli number. You just go there to do that. Okay, now comes the proof. Proof is it just use the combinatorics generating function. You put this skn inside here, but we know this is skn itself is a sum. So what you're going to do? I mean, mathematics interchange two sums, right? So you switch the interchange two sums, you will get this number. It's a geometric theories. Now you just expand. This is the top by Taylor expansion. The bottom, you don't know how to expand it. So you just use the Bernoulli's definition. Put it inside. You get this 2. You put everything down. You're done. So that's basically the proof of the closed formula for the case power of sums up to n. So story up to this point, maybe it's finished. It's done. Everything is done. We have a formula. But the question you still can ask, right? Mathematicians, they're driven by curiosity. The curiosity will be, can I do the negative power, right? But that's completely crazy because you don't want to ask kids to compute 1 plus 1/2, 1 square, because not a lot of denominators put inside. If you start to compute it, you get a bigger mass. I don't believe you can have a closed formula. But at the most, say I'm going to do approximation. Approximation is not a hard part. You could do that way, that way, that way. Okay, so but I really want a closed formula for this thing. So maybe I want to say that, well, for the positive power, I get a polynomial. For negative power, I will not going to get a polynomial. Can I get some other function? Some smooth function, analytical function? Right? You can ask such a question. Polynomial is very special. So this is the question you're going to ask. When we do these negative powers, can we find some nice function to do that? I mean, typical in calculus, what do we do if we have a sum like that? We make an integration, right? Then estimate the error. but that's not closed formula. That's just give you the major term. Then you estimate error there. So their answer is yes, very surprisingly. So you actually can find the closed formula for the negative powers. So this is solved by Euler when he was 26 years old. Euler is born in the same city in the Bernoulli family in the Basel of the Switzerland. That's also the hometown of Federer, right? Roger Federer. So I visited Roger Federer's tennis club because I play tennis. So, but I didn't really get a chance to visit Bernoulli's home and Euler's home. So what Euler doing is that there is for any nice function fx, the sum can be another special value of nice functions. So that's what Euler doing. So it's not necessarily for these negative powers, giving any function. Any function, he will find another nice function. So it's much better than what we do, but take an integration. He actually gives a formula for that. So let's see what Euler doing. Euler doing this thing, he immediately makes the equation, some problem become a difference equation. The question becomes, I give you a function f of x that's smooth, right, analytic. Well, if x is analytic, can you solve this difference equation? So what Euler doing is trying to transfer this difference equation to a differential equation. So first of all, he takes a tail expansion of the second term. But be careful, he uses -1 as a variable. He keeps x there, right? So he got this in. Then he found out this is to the e to the negative ds of x. This is the Euler function. So Euler really knows define e to the x as a function. He also uses it as an operator. He really used that as an operator. Then your fx will be 1 minus e to the negative ds of x. But he want to study, he want to invert this operator. You cannot invert it, right? Because the tail expansion starts with a d there. What Euler do is when I divided it here, I multiply it back. Now this guy, if you take an expansion, you start with the 1 in the first one, right? You're 1 plus something. So you can invert it. Okay, so Euler will invert the differential operator, get this in. Then you get a Bernoulli number. So Euler transfer a difference equation to differential equation. So I always said that the calculus is the tool of science for Newton, but really the tool of art for Euler. Well, then you solve the equation because d means the derivative. You integrate both sides. You integrate everything. All other terms just take if I is positive, just -1. But I has a 0, the first term. This is the term we have in the calculus all the time. But we never thought rather to this term. Right? So this term is the major term when we do calculus, integration there. But this is the term that Euler did. Right? So we forget that any partial sum actually can be not only approximated by integration, can be rather integration plus all other terms as precise as you want. Also, the appearance of the Bernoulli number in Euler's work is very nature. It just inverts some matrix. In Bernoulli, it looks like you put a combinatorial formula put it inside. The Euler, it's just naturally invert. You want to invert this operator, you get a Bernoulli number. So if fx x is the kth power, then you recover Bernoulli formula. So Bernoulli formula is easy to do that. It just because it is infinite sum become finite sum. Right? It's the kth power integration become vanish. So the first one give you everything. But Euler's formula can give you negative power. That's a surprise thing. So for example, if you sum like a harmonic function 1 plus 1/2, 1/3, you get this leading term log n plus this n, as precise as you want. You get the full power series. So this gamma is it is number. If k bigger than 1, you get this first term, s negative k infinity. We know this is convergent. We know it's convergent, so you get all this term there. So Euler really make the huge progress on this sum of the final sum of powers. Well, at this stage, you see, the final sum problems, you have some constant need to be determined. This is an infinite sum. So the question now becomes, what about infinite sum of powers? Right? So we'll put a k there, a positive integer, trying to do this thing. Well, k equals 1, we know this is infinite. In 1735, that's when Euler 28 years old. You will find out Euler only make huge progress when he is even years old. So now the 26, this is 28. With 28, he made the first major contribution to the problem. He solved the k equals 2, which was called a Basel problem. So this actually the problem was considered by the two older Bernoullis. Euler is a good friend with the third Bernoulli, that's the son of Johann, Daniel Bernoulli. So this is the sum he figured out how to do this thing. He actually calculated all the, make a lot of approximation, finally figure out this formula. So Euler's solution is really, so I just describe a little bit what's Euler doing with the solution. Okay. Yeah. So what Euler doing is that he studied sine x. He studied sine x like a polynomial. So what does that mean is that, first of all, he's trying to figure out, we know sine x is 0 for all the integer multiple of pi's. So then Euler probably figure out, this probably means that sine x has a product formula like that, right? I mean, like a polynomial. If you know the roots, you can decompose it. But Euler also knows the Euler formula, right? Because Euler knows how sine x related to exponential function. You get this formula. So now the great thing is, you know, you have a product formula. You have the additional formula. Now you can compare the coefficients of the every terms of x, right? So you compute the coefficient x, the third power of x, both sides. What do you find out? The first guy gives you the sum of the k squared, pi squared, but there's the roots there. This side gives you 1 over 3 factorial. Right? So that's something we use every day when in elementary school or middle school, but we are done for polynomials. For Euler, it's brave enough. He did it for any analytical function. But there's some, I mean, Euler didn't really prove this formula. He just calculated it. So this took Euler another maybe 10 years trying to figure out how to prove the formula exactly. So anyway, this gives the proof of sum that has a power. So the argument also applied to symmetric functions, the 1 pi squared, k squared, because the previous one, the roots always square here, right? Always square here. So you can trying to use Newton's method to get out the powers of the roots, right? Then you get another formula. You get what I said, you can give two expressions for this thing. You will find out this formula there. So Euler not only prove the sum of the square of the negative square of integers, he also do for all the even negative integers. So you can do it for the power, 6th power. But interesting thing is there's no closed formula for outer power. We don't know. We don't have any closed formula for third power. And we don't know have any closed formula for fifth power. So one guess is that all these order powers generate some new numbers, which is algebraically independent of pi. For even power, you always get a pi there. For odd number, you're supposed to get something number which has nothing related to these pi's. But nobody knows how to prove it. Only very recently, they proved this guy actually is an irrational number. But it's far away to understand how this number behave. So the algebraic property of these numbers. Okay, so the 28, now finally get 30 years old. What's Euler doing with his 30 years old? Well, Euler cannot stop to study this thing. He already became really famous after he solved the Basel question, but he cannot stop. He just found that this is really amazing thing to do. Well, he started thinking about the product formula. You see, Euler's really contribution started sine x, right? He just used sine x two different ways, right? Euler said, well, I can do for sine x, I probably can do for zeta of s as well. So he found a product formula. Product formula, if you have a function which has both has a product formula has addition formula, you will prove some big theorem. That's what the Euler told us. So zeta definitely has a product formula. That's what Euler did. I think this is probably not really surprising. The surprising thing is how Euler used this stuff. Then he took the expansion of log zeta x on both sides. He got log zeta s equal to this thing, the plus sum of the p to the s plus over 1. Well, the significance of this formula is that you take s equals 1, you find a sum of primes equals infinity. That's amazing stuff. So what I'm trying to say is, there's a product formula. You apply the product formula in a rather easy way, you prove that the sum of the reciprocal of primes is infinite. So this particularly implies that infinitely many primes. So this is an analytical proof of infiniteness of primes. So the elementary proof we know is proved by Euclid 300 BC. But Euler's proof is a really new chapter of the number theory we call the analytic number theory. Analytic number theory starts with this theorem because his proof is much strong. So that's somehow is the pre-birth of the Riemann zeta function. So Euler not stop it. Euler, he extend the zeta x by the following method. He wanted to say, well, s is bigger than 1 is convergent. Well, s is less than 1 is not convergent. He feels not happy about it. He still wants to study zeta of s. He wants to study zeta x between 0 and 1. The trick he doing it, he applies some small trick, make this one to be conditionally convergent series. Now this side you need only convergent when s is bigger than 0, right? It's much better. Before you need s bigger than 1. Do you realize that when you go to a p series, it was a very small trick. It becomes a conditional convergent series. So now you can start the values when p less than 1. That's our calculus teacher always forbidden us to do that, but Euler did it anyway. So Euler, he got a formula for zeta s. For any s bigger than 0, he defined this to be zeta s. Right? Because this is convergent for any s bigger than 0. This is some number. Well, so this is his definition. It's not a bad definition. When s close to 1, actually, if you do this thing, you will get 1 over 1 minus s, then use the L'Hopital rule, you actually can find expansion of that x near s minus 1. So that's actually what Euler figured out, a asymptotic formula for zeta s near s equals 1. Because when s equals 1, this becomes right? I mean, this is both sides get a log of n, log of 2. Log 2 cancelled, so you get this formula. Then Euler, not finished yet. He said, well, for this variable between 0 and 1, he done it. He wanted to do when s is negative. That's crazy, because he wants to study the series 1 plus 2 to the s plus 2 to the s, where s is positive. Euler want to make a meaning for these numbers. What's he doing that? What happened is the conditional, I mean, the alternative series divergent. So Euler said, that doesn't matter. If alternative series divergent, I'll put x squared, x cubed inside. Right? I know the radius convergent less than 1. So when x is less than 1, it's convergent. If he's lucky enough, this sum has a beautiful formula that he put x equals 1 inside. That's what Euler doing. Then in 1939, Euler 32 years old, he found this formula. He compute the zeta values, I mean, infinite sum of positive power intersum, these numbers. So in other words, he proved that 1 plus 2 up to 1 to infinity be negative 1/2. That's Euler proved. That's crazy. He proved 1 plus 2 plus 3 is negative 1/12. And he proved that 1 plus 2 squared plus 3 squared, sum all square equals 0. Use his definition. He proved that the cubic power together is 1/120. He proved the fourth power equals 0. You see, all even powers except the first one equals 0. Using his algorithm. I can tell you how to prove this formula. It's very elementary. Oh well, this you want to do this then. By Euler definition, you first write this thing as this thing. It's still stupid because every term goes to infinity, right? Then Euler interpret this term as put x inside, right? Reinterpret it. Once you reinterpret it, then this becomes x over 1 plus x, take the differential operator many times. Well, then you take a sum of the same, take exponential, whatever, you will go back to Bernoulli numbers. So that's what Euler proved. Okay, so well, my lecture that after Euler, he done, I mean, he probably his time is the calculus was not really developed that much. They use everything he know. Basically the college calculus, he can do so much for the zeta values. The next big progress has come to Dirichlet. So what Dirichlet know more than Euler is that he knows Fourier transform. So now I just want to see that if you know Fourier transform, how can you do for the zeta functions? So study of the error function, zeta function is always associated to how much we know about the calculus. Okay. Dirichlet proved a theorem. It's a famous theorem. Is that for any two integers, then infinitely many prime p in the residue class mod n. For example, they make infinitely many primes when you mod 4 become 1. Also infinitely many primes when mod 4 equals 3. That's Dirichlet proved. And his method to prove the theorem is exactly the same as Euler. He trying to prove that reciprocal of these primes is infinite. So what's he doing? What's the Dirichlet doing that Euler doesn't know? That he knows Fourier transform. It's not only in the Fourier, he really knows Fourier transform. He applied to finite group. So he starts with a finite group. You just take the L2 functions. The G is a finite abelian group. Usually Fourier transform we're done the real numbers, right? The real numbers have the character exponential functions. So we know every spectrum we can write down the spectrum. But this philosophy is exactly the same proof applied to other abelian group. So you put an abelian group, you take L2 space, they become finite dimensional Euclidean space. Then this space is also expansion by characters. Characters are like exponentials. Then every function you have a Fourier expansion can be written down this way. It's the same. It's the same sense. You don't really need to. It's just something like real numbers. And the Fourier, the Dirichlet apply Fourier transform twice. First for additive group, second for multiplicative group. Multiplicative group means that if you have a ring, if you have a ring like real numbers, then you think about real numbers. Real numbers summation become a group, right? So this is additive group. But also if you take a zero out, take only the positive numbers, the multiplication become a group. The Fourier transform for multiplicating group for positive numbers, we have a different name called Maillard transform. But basically it's Fourier transform, right? Because the exponential function. So Dirichlet apply G there. So if f delta A inside, you use an additive Fourier transform, you get this formula. Then say I want to compute the reciprocal primes in some residue class, then you just bring this data inside. In the top, you apply Fourier transform. You get this in. And this second one is a character. Then when chi equals 1, there's infinity by Euler. Euler done already. So he needs to only show that all other terms is finite. Because he wants to show this is infinite. We know already one term is infinite. We hope other term is finite. Then we are done. Right? So what Dirichlet doing is that he done exactly the same way as Euler. Just copy whatever you copy. You copy it, you get this same, exact same formula as Euler. Euler, only difference chi p is 1. But for Dirichlet, it's not 1. He gets his formula. So this is called a Dirichlet error function. That's the first time error function was introduced. This error is for Leronde. Because the first time the chi is a quadratic symbol, the Leronde symbol. So Dirichlet called this the error function in name of Leronde. Then he has the exact same formula like that. So to prove Dirichlet theorem, it suffices to show that this error function, the value at 1 is finite and non-zero. This is what the Dirichlet is doing. Okay, so how can I do compute these error values? You see, then Dirichlet apply the Fourier transform the additive group. So, where additive group, same thing. You have a Euclidean space. It can be written down as the sum of characters. So then this chi was a multiplicative character. You can write down as the sum of the additive character. So this you play addition. You get this formula. Once you get this formula, your error function can be written down as additive error function. So this psi is the additive character. So psi n plus 1 equals psi n times psi 1, right? So you get this n. But this psi 1 is psi 1 to the nth power divided by n. So you're just using the usual formula, Taylor expansion, for the logarithm function. You get this formula. So in this way, Dirichlet actually calculated explicitly his error value at 1 by applying additive Fourier transform. Well, then it's immediately shown this is non-zero finite. He proved Dirichlet theorem. So what Dirichlet knows a little bit more than Euler. He knows that you can do Fourier transform. Well, Fourier was not born yet when the Euler time, so Euler doesn't know the Fourier transform. For example, n equals 4, 1 minus 1/3 plus 1/5 plus blah blah equal to pi over 4. But this we can done by some other method, right? But basically Dirichlet's theory generate this formula, right? They finally come to Riemann. Riemann is a mathematician, and somehow he wants to solve a problem by Gauss. Remember when before the Euler showed that the reciprocal prime is less than is infinite. So then the question becomes: you're given a bigger interval from 0 to x, how many prime be inside? So if we go to then Euler somehow the Gauss somehow done by hand. He computed 20 pages of primes. He computed each prime. Then he found out how many prime in the interval. He took a notes. It's really written very explicitly. Then he made a conjecture that so the number prime in the bigger interval has a closed formula. So that's a bigger problem there. Then the Riemann took over the question. He wanted to do something. Well, Riemann just he knows complex variable, right? And the Euler doesn't know. So it's not difficult just to extend this function to be a variable, real part of s bigger than 1. You get this thing, Euler product. What Riemann want to do have two things. First of all, he really want to apply original Fourier transform, not the Fourier transform that Dirichlet is doing. Dirichlet is doing the baby version of Fourier transform. The first thing. Second thing, Riemann really want to study not Euler's product, the really product formula. So Euler product formula is give you analytical function. I mean, if you have zeros, you hope you can decompose your your analytical function as a product of zeros, like a polynomial. Like what's the Euler done for sine x, right? Euler for sine x is write down really run all the zeros, that take expansion. Riemann want to do two things. First of all, he want to apply Fourier transform, original Fourier transform. Second thing, he want to study the zeros of the functions. He hope the two things can give you something. Well, the real Fourier transform, well, you see, this is the additive character, right? Because the additive character means that the addition of the function become multiplicative. This is a multiplicative character. So first of all, the Fourier expansion of additive character, I don't know which one you want. Which one you want? If you the multiplicative character, if you want to do the Fourier transform in terms of additive character, you will get something called a gamma function. So gamma function basically is the connection between two operational real numbers, addition and multiplication, right? But it's written down in a function analysis way. But this is why the gamma function is such an important function, because you're trying to say the secrets of two operational real numbers, addition and multiplication, right? So because one of them is addition, this is the multiplication. So we do this way, you write on the Cauchy of S, because so the one thing we difficult to study the Euler zeta function, because the bottom is addition 1. You hope some way you can transform to the multiplicative one, transform to the additive one. So this is a small game to transform zeta function to something like that. So the sum of a Gaussian. So this is called a zeta function. Then you write this sum between 0 to infinity. You write two things, 0 to 1, 1 to infinity. Just break it down. And you use the Boson summation formula for this guy. Then you get a closed formula like that. It's a really good exercise to check your Fourier transform. So you done this Fourier transform, you write this zeta function as a very close formula, this f of t integration are like that. You plus these two terms. The two terms is because there's something to do with integrating 0, 1, some function you don't want to bring inside. This is Riemann's closed formula. So this gives a meromorphic continuation of functional equation of the Riemann zeta function. It's one of the biggest theorem. about the zeta function. And Euler, as I said that, Euler said everything is very natural from 1 to infinity. When x is less than 1, he used a lot of tricks trying to define that. And the Riemann didn't do it. Riemann just wrote a very natural way, defined for every complex number. And of course, I mean, it's a very funny thing, Riemann using the Euler's gamma function. That's probably the key thing he's used. He still used something what Euler doing. So this actually also explain that, as I said, when Euler do the work, it's a very funny thing. He did the sum of the powers, both positive and negative. And they found the two different ways they related to each other. Right? Like, I mean, the positive power and negative power somehow relate to each other. That's really surprising. Right? Now, this phenomenon only explained very naturally after the work of the Riemann. Okay, but Riemann not stopped yet. After Euler, everybody want to study the product formula. Okay, that's what the Riemann doing. So together with Euler product formula, there is another product formula in terms of zeros. Well, I mean, you have some functions in terms of zeros. So now you have two product formula. One product formula is about the zeros of your function. Another product formula is about the primes. So there must be a relation between zeros and primes. So the Riemann just made a hypothesis, all the zeros of cosine x lines the real line 1.5, because that's the way he can prove the Gauss conjecture, that the number of primes lives in a number of primes less than x, exactly given this closure formula. And if you read the Riemann's memoir, he actually made a calculation of this thing. He tells you how to calculate, how to verify the conjecture. And his verification is very simple. He's really use the complex variable. So for real variable, there's no way you can do that. If you have a complex variable, if you want to check how many zeros in the line, actually it's easier. The reason is calculus can give you a lower bound. Why? Because if you have a function, you check how many sign changes, right? You get a lower bound. But Cauchy equation can give you upper bound. The reason is if you have f, if you know that zeros, f prime divided by f, you integrate and you make a bigger circle there, then give you upper bound. And the Riemann exactly use this method to show that upper bound and lower bound are the same up to the bigger interval. So he showed that in these bigger numbers, that there's in a certain bigger interval, all the zeros must be in the line, right? I mean, he proved on the line not because he calculated every zeros. He showed the lower bound and upper bound. Okay, so at this point, I probably want to introduce the general notion of Dirichlet error series. Right? We should not stop there, because the Riemann zeta function is just the summation 1 of ns power. Right now, you can do much more. It's just summation of an ns power. An is just some complex number. But in terms of if you think of what the Riemann Euler doing, looks like one thing you want to do, you want to have a product formula. Right? You want to have this thing, sum of product P. But in their work, it's very simple. There's a product formula, each affects the geometric series, right? 1 minus p to the s. Now maybe you should not. Maybe you relax condition a little bit. What do we relax is that we'll have the second guy to be a polynomial. That's also good enough, right? So the polynomial p to the x, you want leading term to be 1 because you want to be convergent. And you want a degree to be fixed. You don't want to be crazy. I mean, some degrees 1, some degrees 3, it goes to infinity. This is not hard, right? If you think this is not a hard business, because you can start with any polynomial, you take a product, you get this in. You get Dirichlet series. The next requirement is very hard. You want this guy have a meromorphic continuation of the complex plane. This is not easy. How can I can randomly construct this product, but how could I know this will have analytic continuation to the complex plane and have a function equation. These last two guys are almost impossible to construct by elementary method. So this is a beautiful definition, probably not easy to find any example. I mean, the exam must, from analysis, it probably is nowhere to find an example. So all the example only come from, so the basic number theory has two different sources to get these error functions. One's using algebra, one's using analysis. So I give it two different ways. So how to find the general error series? So I give you two examples. One is by the purely algebra. For example, instead of rational numbers, you can study a number field, like for example, Q of I, Gaussian number. Once you have a Gaussian number, you also have your own primes. You can form your own zeta function, right? So you will get this thing, and you can show, that can show that this has a meromorphic continuation, has a function equation. Not only that, he also can compute the residue at s equals 1 given by this formula. And this formula carry a lot of information about number fields. And the heck then done by Dedekind work on number field. Heck introduced something called a Gaussian character. Gaussian character, for example, when you study the Gauss problem is counting how many primes from bigger interval. If I study Gauss number, that's very interesting. But my prime is not in the interval, right? In the plane. Plane is so I can count, give you a region, bigger angle region, whatever. How many primes in the region in a complex plane? Okay? That's such a question. If to that question, you cannot use the Riemann, the Dedekind zeta function. So heck figure out to introduce another chi there. The Dedekind's method and the Heck's method were reformulated by Tate using harmonic analysis and ideas. So it's basically, so this is the two different way to generalize these Dirichlet error function. One is using algebra, so in modern terminology called Galois representation. One is analysis, is harmonic analysis on groups, so we call it automorphic representation. So there's so now I talk about the future for a few minutes. So the future says the Lagrange program basically say there's two very different way of construction error function. Actually the same way. They construct the same kind of error function. Probably analytic way slightly more than algebraic way. So the basically two to same method. So at least all the algebraic way construct this error function can be redone using analysis. So analytical property of error function, if your error function is constructed using analytical way, then you can do the same game like a Riemann, right? Boston summation from a lot of things to study the properties. So these properties, you still have a Fourier analysis on two different groups. Is GRN, that's n by n, the multiplicative group. Another one, the matrix group. Matrix group is simple. Matrix group is just the r to the n square, right? So the Fourier analysis, second one is easy. The first one is hard. But the whole point is that you want the first guy x the second guy, take the Fourier, take the expansion. So the Galois representation, the very example Galois representation come from cohomology algebraic varieties. So if you study number field, you study variety. Variety means you give you polynomial equations defined over Q. These equations naturally give you some Galois representation, a cohomology. I mean, for example, if a variety defines real numbers, then we have a Betti cohomology. Your variety has a complex structure, you have a Hodge structure, you have a Betti cohomology with some Hodge structure. If a variety defines a number field, the Betti cohomology will carry so-called Galois representation. So these are nature examples to do this thing. So the game of the error function that starts with Euler now become a major tool to study Diophonic equations. Because to give you any Diophonic equation, you have error function there. So there are many conjectures in number theory and arithmetic geometry. So the most mathematicians are driven by these conjectures. For example, the special values of error function about the Diophonic property varieties. For example, BSC conjecture, tether conjecture. And basically, the Riemann hypothesis, Lagrange program, a special value of error functions, are three major topics in number theory and arithmetic geometry in the 21st century. So this is what I'm trying to talk about the future. But of course, there's very little progress are made by these three things. But probably the most of people in the major university in number theory, they work on one way, other way, related to these three problems. So maybe should I stop here?
Thank you, Professor Zhang. Now I have a question section. Any question from the audience? Yes, please. Yeah.
Hello, Professor Zhang.
Yeah.
I think I've heard of something called a geometric Lagrange program. So how does it naturally come up in the study of the Lagrange program you have introduced here?
Yeah, so, okay. The short answer is no, I don't know. But I can speculation is that they usually study two different groups. For example, your geometric Lagrange program is you replace number field by other field of a variety, right? For example, C of T, for example. Now, then you have a group G. So basically, you want to study to category two things. One is a Galois representation to the dual group of this G. Another one is a G local system. This is Samson's G local system, the G Lagrange dual local system. Other thing is what they automorphic vector bundles of other things. So the basic study two groups. But the really big difference between that subject and this subject, they don't really produce any error functions. Well, it's a one extension of their Lagrange program, and sometimes useful for real Lagrange program. For example, the work of Shou-Wu, for example, he was studied with the geometric Lagrange program. He got application to arithmetic Lagrange program. Also, geometric Lagrange program has some relation to physics, and Witten has some idea how to relate the geometric Lagrange program to some mirror symmetry. So, but that's completely different area. I have no idea. I only care if they really found some applications to their arithmetic term. Only until very recently, their program sometimes has some applications to number theory.
Thanks for your answer.
Any other question? Well, there's a lot of students at age of 26, 28, 30, something, right? Can yes, please.
So any new analytic method to study these kind of things? So you mentioned calculus and then Fourier transform and then complex function theory.
Yeah, basic. Yeah, so I mean, I didn't talk about the present. The present really study error function already belong to three different categories. So people do analysis, really complex analysis, right? And of one variable. You want to study only the S part, right? So that's the analytic number theory. They have a different way, truncation, or all the different method. They also combine it with modular forms, right, to get various estimates. For example, how many zeros in this vertical line, and what is the space between them. So the Katz-Sarnak has a lot of idea about a lot of things there. There's a group of people, as I say, the more I have 3 different problems. That's called Riemann hypothesis. Just want to study zeros. Then, of course, the Lagrange program. Then there's a group of people study automorphic forms and the Gauss representation. There's also 2 different groups. One group just study harmonic analysis of GRN, right? Laplace, Lie group, Lie algebra, Laplacian operate, right? Locally Hermitian symmetric space, this kind of thing. That's a more global analysis. And also there's the Gauss representation people that study congruence. The congruence is interesting is that the Gauss representation itself is not complex in nature. It's periodic in nature. So that gives you a very interesting phenomenon. So when we study harmonic analysis, we decompose space in the spectrum in a complex world, right? But if you're lucky enough, the coefficient happen to be rational numbers. You also can consider the periodic property. The funny thing that's discovered by many years before by Atkin and Sayre, even Ramanujan has some idea that the complex spectrum in our world are perpendicular to each other, right? Once they're perpendicular, we consider them independent. We have no relation. In periodic world, they're actually the continuous family. Since the continuous family, they're going to produce new limits. So the limits are called a periodic modular form or periodic error functions. So that's the way Newton doing. And then the new method was really fully developed by Andrew Wiles. He used this method to prove Lagrange program in the simplest case for elliptic curves, and by Richard Taylor to prove the new cases of the Lagrange program. So this is a really completely new direction of the thing. So it's not a harmonic analysis of the real numbers, the periodic value of functions. So this is a new direction. And the third direction, I want to say, is the relation to the algebraic geometry, right? So this, we study intersection theory of the algebraic cycles and varieties, right? So there's a special value. And very recently, for example, I mean, the special value, for example, if we, when we study Riemann zeta function, you have a leading term, 1 over s minus 1. Naturally, you can ask what's the second term. Second term is gamma function, Euler gamma function. You could ask what's the third term or fourth term. This term we could never dare to think about it because our analytic tool is far from good enough to handle this kind of question. But recently, there's 2 young guys, Zhang Wei, Yun Zhiwei. They, in their sentence case, in function field case, they have a closed formula for every Taylor expansion of this thing. But the tool they use is really, it doesn't apply to number fields. They use the moduli of Stuka. It's a far beyond something we understood. So so your question is a very difficult question. It's basically the full developments of the current. So that's why I want to mention the present part. You know, we have no idea what's. I mean, it would be a dream. We can understand that the Taylor expansion of the Riemann zeta function, what these coefficients, what kind of meaning it have.
Okay. Yeah. Any other question? In the back. Yeah, maybe it's young.
So thanks for the very interesting talk. So I can understand only maybe the first 20 minutes. So my question is.
So up to Riemann?
Yeah. No. When you mentioned there's a formula for sum when the index is even, right?
Yeah.
It's pi something. When it is odd, then you don't have a cos formula.
No.
Okay. So my question is, if you assume the number when the index is 3,
Yeah.
is something, so can you represent the other number by this number?
No, that's exactly the conjecture. The
Okay.
conjecture is that all other numbers are algebraically independent from each other.
Independent of each other.
Algebraically independent.
Big-
So there's no way you set up a algebra equation. So like even is always
Pi.
power of pi,
Yes,
Russian
power of pi.
numbers. Otherwise, it's not. So in other words, the study trigonometry function is not good enough for this kind of thing. Because you see, basically with Euler doing this thing by sine x. You need to create some other function to study its other numbers. But I give you some idea. Okay, that's something. Okay, you ask a good question. So you reminded me something is the following. So it's a functional equation between the s1 minus s related to the other number, a even number that's following the other positive power to the even negative power. But even negative power, I say, is already 0. So it means that related to the first derivative, right? So that's our first derivative. This first derivative actually related to some arithmetic intersection numbers to some Shou-Wu varieties in some simple case. So they do have some meaning. So it's something called heights. Yeah, so it's just it's the next level thing. Yeah.
Okay, thank you.
Okay. So maybe you can give a homework for your student to solve this equation. Any other question? Yeah. Yeah. So Professor Zhang will be here. So if you really want to ask a question, you can ask him probably after the lecture. So now let's thank Professor Zhang again.